Hello, I'm Rex Childhouse, and because things on the internet seem to lose their date references pretty quick, today is May 14th, 2024. It's a Tuesday. I was in our local library here in Ramona and was looking for things to read, and we are in the very near future doing an astronomy train ride to go out to an area that has zero light pollution and look at the stars. So I walked over to the astronomy section just to see what was there. There were a grand total of 3 books, and this is the one I picked up. And the title just got to me, and it is Under Alien Skies by Philip Plait, PhD, author of Bad Astronomy. And it is a sightseer's guide to the universe. Now I'm going to flip through here and I'm going to read you the chapter titles and give you a little history. The first place he takes you is the moon, which is kind of cool, and he explains what you're going to have to do to walk around the moon, live on the moon, what your hazards are, what your pleasures are. Then we're going to go off to the red planet Mars, which is kind of cool because we go out and view Mars every once in a while. Then we're going to do asteroids and comets and have some fun with those. Going to go off to Saturn. I love Saturn because we get really good views of Saturn and her rings from our backyard with our small telescopes. I wish we had a bigger telescope, but that's okay. We're going to go off to Pluto, and that's a fun one. Then we're going to go off to planets around red dwarf stars, which is interesting, and move on to planets with 2 suns, and that's Tatooine. So if you are a Star Wars, Star Trek, Battlestar Galactica, any of the space sci-fi series, this particular chapter is like really fun. Globular clusters, which are like nebulas and whatever, and then we move into nebulas, and then we go to black holes. I will tell you in all honesty, if I understood 25% of this book, I would be overstating the fact. I enjoyed reading it. I probably understood 10 to 15% of it, could probably explain 10 to 15% of it. Really enjoyed the chapter on planets with 2 suns, Tatooine, Star Wars, and he makes some comments about that. They're all in support. There's no derogatory stuff in there. And he also explains black holes. And I reference later in the video a movie called The Black Hole, which is a Walt Disney production, and some of the a couple of the images from it, and it's interesting. So quite honestly, I enjoyed it. If you love astronomy or you're curious about your universe, your solar system, this might be a interesting book to pick up if you can get it, and I enjoyed it. So let's get on with the book review, because I really enjoyed this book. Thanks for watching. Hope you enjoy it. In Star Wars Episode 4, The New Hope, the first one released, I think was 1977. Don't hold me to that. Might have been a little later or earlier. Luke is standing on Tatooine, and he's watching his 2 suns in his solar system set on the planet of off in the horizon of Tatooine, and he's going to now go into his house and into his shelter. And this is not an uncommon event in the galaxy. There are a number of binary 2, 3, 4, 5 star solar systems. So we have 1 star sun in our solar system. Many others have multiple stars, and because of that, the math associated with them gets very interesting. On page 184 of Under Alien Skies by Phil, he identifies the 2 primary, I guess they are, principal, or whatever you want to call them, types of orbits for a planet in a binary system. And the one on the left, where the planet rotates, orbits around the primary, is the S system, and the one on the right, where the planet orbits both systems, is the P system. And he explains how these work, and it's kind of interesting, and I'm going to show you some better detail. On page 193 of my copy of Under Alien Skies, Phil gives you the terms, the proper terms to be used with the S type orbit pattern. I'm going to take this into a little bit more detail, and it's in the book, and try to explain what would make this really interesting. This is one of the graphics that Phil has in his book. It's on page 195, and it kind of explains some of the interactions between the star and the planet that's orbiting it. I'm going to go into a little more detail than shown in these, and it's in the text, and I'll bring to light some interesting scenarios. Working with the S orbit scenario in a binary system, and under the assumption that the orbiting planet does not rotate on its own axis, we have in position A, the one to the right of the primary, that both sides, both hemispheres of the planet are illuminated by the secondary star. And part of the complications of this is, how bright is that secondary star? How far away is it? How bright is it? How much does it illuminate? Just assume that it illuminates the planet to some degree, enough to leave a shadow. As it moves to position B, the hemisphere, the lower hemisphere of the planet, is illuminated primarily by the primary star, mainly by the primary star. It is also, the right-hand hemisphere is mostly illuminated by the secondary star, and the upper left hemisphere is not illuminated by anything. So only about maybe 30% of the planet is unilluminated. That odd 5% is the upper right hemisphere's left-hand corner, which is kind of shielded due to the geometry. As the planet moves to position C, the one to the left of the primary star, the left hemisphere is not illuminated at all. The right hemisphere is only illuminated by the primary, so it doesn't have that secondary heat source that it would receive from the secondary star. As it moves to position D, the one on the bottom of the primary, the upper hemisphere is heated and illuminated by the primary star. Most of the right hemisphere is heated or illuminated by the secondary star. Again, that bottom right hemisphere near the center is kind of shielded, and the bottom left portion of the hemisphere is not illuminated by anything. Because of these irregular, inconsistent, dual heating, differential of heating issues, this planet's going to have some very interesting weather conditions. And if it has fluid water, the tidal conditions are going to be horrendous. Maybe that's what shows up in the later episode of Star Wars, where Rey is going over to the crashed Empire, and I don't remember exactly what model it is, with the wave finder. Maybe that's what played into, maybe this is what played into that scenario. Let's add some more fun to this S orbiting scenario, where the planet orbits only the primary star, and the secondary star does have the ability to illuminate, to heat that orbiting planet to some degree. First of all, in position A, I'm going to guess, and I'm not a professional at this, I'm going to guess that the distance between the primary star and the planet is going to be greater when the planet is at position A than when the planet is at position C, because the secondary star is going to be pulling it with its gravity. Even though the gravity may not be as great as the primary, I think that secondary star is going to have an influence on the shape of the orbit. So in position A, the entire planet is illuminated, left hemisphere by the primary, right hemisphere by the secondary. As it rotates counterclockwise on its own axis, and it rotates counterclockwise around the primary star, the now blue hemisphere is totally illuminated by the primary and partially illuminated by the secondary, and the upper right portion of the right portion of the red quadrant is mostly illuminated by the secondary. We're assuming the secondary has enough brightness and is near enough to at least cast a shadow. But the upper left portion of the hemisphere is going to be in darkness. A portion of that upper right hemisphere near the terminator line, I believe it's called, is going to be in shadow because of the angles of this. So we're just making some assumptions. As the planet orbits into position C, the left hemisphere, the red hemisphere, is going to be in total darkness because the primary will be blocking out the secondary, and only the right-hand hemisphere, the blue hemisphere, is going to be illuminated by the primary. As it rotates down to counterclockwise down to position D, the blue hemisphere will be illuminated by the primary, and the right-hand portion of the planet will mostly be illuminated by that secondary star. But again, that bottom portion near what would be the vertical terminator line, I believe it's referred to, is going to be kind of shielded due to the geometry here. But the bottom left quadrant is going to be in darkness, and again, because of the surface heating, if there's moisture, liquid moisture on this planet's surface, the tidal issues because of these gravitational changes, the weather issues are going to be really, really interesting. The other option here is a P-style orbit where the planet rotates orbits around both stars, where the primary and secondary star are both inside the planet's orbits. And this one is back to fun. And once again, I'm not a pro at this. I'm not educated at this. If I told you I understood 25% of this book, it would probably be a gross overstatement. I found it extremely interesting. So we have the primary, we have the secondary, and we have our orbiting planet. And again, I've cut them into blue and red hemispheres. I should have probably cut them into quadrants for us, so we could keep the colors apart. That's okay. When we start at position A, that's the one at the extreme right side of the graph, the left hemisphere, the blue hemisphere, is heated by primarily a combination of the primary and secondary star. The primary star is eclipsed by the secondary star, so there's probably portions of this planet, and assuming the size, that are in shadow. Maybe all of it. It all depends. But as the planet orbits counterclockwise, the eclipse will change. The other issue here is, how do these two stars interact with each other, because the stars may be on their own orbits. We're not going to get into that. I will just tell you that if you add that to this mix, it gets really, really fun. So our planet is going to orbit again counterclockwise. When it goes up into position B, a significant portion of the planet, and we're working on the assumption that secondary star can not only heat but illuminate, not only illuminate, but heat the orbiting planet to some degree. And we'll see that probably 90% of the planet is illuminated and heated by the primary and secondary star. Obviously, the primary star is going to focus on a significant portion of the lower left portion of the planet, with the secondary being the lower right of the planet. But the top of the planet is not going to get much heat at all. It's not going to get any light. It's shielded by the mass of the planet underneath it. When it moves counterclockwise to position C, only the primary will be illuminating the right-hand hemisphere, and the left-hand hemisphere is going to be in darkness. Once again, no heat from the secondary, and this is going to be an interesting scenario. Should be relatively simple. As it moves down to D, position D at the bottom of the graphic, we come up with that scenario again where the primary star heats a significant portion of the planet, secondary star heats a significant portion of the planet, but the lower portion of this, not the star, the lower portion of the planet is not heated, it's not illuminated, so it's not going to get much heat. Because of these differences, as this non-rotating planet goes around the primary and secondary stars, we're back into some really interesting tidal weather scenarios due to dissimilar heating on the surface. Heat and water holds heat really well. It's a heat sink, and that's why we have coastal onshore, offshore winds, coastal winds, because of the differentials. 1/10 of a degree of ocean temperature change is a major heat difference in the atmosphere. Interesting scenario here. And the last scenario in this P type orbit system, where the planet orbits both the primary and secondary star, we're going to give the planet rotation on its own axis, and that's going to be counterclockwise, and it's going to rotate, orbit counterclockwise around the primary and secondary stars as a group. And in position A, the one to the right, the left hemisphere is heated primarily by the secondary, with the primary star partially in eclipse caused by the position of secondary star, so you'll have differential heating. As I said before, as the primary and secondary stars orbit each other, and the angles and the timing, how in this position, how the left hemisphere is going to be illuminated and heated is going to be determined on the exact position of the primary and secondary stars. When we move counterclockwise to position B, the one above it, the primary star is going to be the primary illuminator and heater of most of the planet, of half of the planet, and the secondary star, and we're working on the assumption that secondary star can provide illumination and heat to some degree due to distance and brightness to another portion of the star, of the planet, but that top portion, probably 20%, is going to be in total darkness, and that's going to be a different portion than was in darkness earlier. So we're going to now rotate off to position C, and position C, the secondary star is going to be totally blanked out by the primary star, assuming the primary star is bigger, and it usually is, and only the right hemisphere, only the blue hemisphere, is going to be heated by the primary. So the left hemisphere, the red hemisphere, is going to be in darkness. As it comes back around to position D at the bottom, the blue hemisphere is now going to be totally illuminated by a combination of primary and secondary, and maybe a portion of the red hemisphere might be illuminated depending on exactly how it sits in this orbit. Maybe it's not. But this combination, because the planet is now orbiting on its own axis, rotating on its own axis, and the planet is orbiting a primary and secondary star, which are amongst themselves shifting positions in an orbital pattern, we get back into a scenario where, due to the surface of the planet, whether it's got water, whether it's got atmosphere, what gases are in it, how does it absorb the illumination and the heat from its primary and secondary star. These are causes that are going to make weather forecasting on this planet really, really interesting. And I think I'd actually like to be a weatherman on this planet. Anyways, that's my guesses, my explanation on Tatooine and Luke Skywalker, Star Wars. If you are a fan of Star Wars, Star Trek, Battlestar Galactica, this is the sort of stuff you're going to find as you cruise the universe, and the universe is very, very big. On page 272, Phil brings up something I probably can't pronounce. Relativistic beaming. And supposedly Einstein explained how this happened. Quite honestly, it's Doppler shift associated to light. Light, and it doesn't matter whether it's UV, infrared, visible, what color it is, radio waves, all these things have waves. That means they come at you in a plus and minus. They're cyclical. They come as pulses. This includes sound. And in Doppler, the Doppler effect is, as a train is coming at you, if you're standing still, as a train is coming at you, when it blows its horn, and it's going to keep its horn blowing, as it blows its horn when it's 100 feet away, the sound wave has to travel 100 feet to get you. The train now moves to 90 feet away, horn is still blowing. The sound doesn't take as long to get to you, so the sound catches up, it gets closer in wavelength, and as it gets to 80 feet, it doesn't have to go as far, so it gets to you, quote unquote, quicker than per feet distance from the 90. So what you hear is, you hear the waves hitting your eardrums in increasing frequency, increasing the pitch of the horn. The horn doesn't change pitch, the horn stays pitched. The horn passes you, the train passes you, and now we have just the opposite problem or situation. As the horn blows next to you, you're hearing it at its natural pitch. As it's 10 feet past you, the horn sound now has to travel a greater period of time, so the horn pitch sounds lower. It's not actually lower, it just sounds lower because of Doppler shift. When it goes an additional 20 feet, so when it goes an additional 10 feet, so it's 20 feet away, it has to travel that additional distance, so the horn pitch goes down one more time. This is Doppler shift. Now the same thing happens, as Einstein explained it, with light. Light is a wave. As light is coming at you, the first beam sent to you at 100 feet has to travel that period, that distance over time, and speed is constant. As the light source moves to 90 feet, it doesn't have to travel as far, so it gets to you, quote unquote, quicker, same speed, but less distance. So the light seems to get more intense as the source gets closer to you. However, going the other way, once the source passes you, the first beam of light past you has to cover, say, 10 feet. The second beam of light has to cover 20 feet, and because it has a longer distance to travel, it has more time. It has to take more time, so it's going to be dimmer. So a light coming at you gets brighter, a light going away from you gets dimmer. This is Doppler shift as applied to light. And Doppler shift applies to anything that has wave. So any light, from visible to invisible, radio wave, whatever, has Doppler shift effect to it. I'm amazed they don't bring that into the scenario, but that's up to them. Phil also brings in a closing chapter of the book, Black Holes. I don't fully understand black holes. I watch a fair amount of science fiction. I know how science fiction depicts them, and this particular image is taken from a Disney film called The Black Hole. It has Ernest Borgnine in it and a number of other stars. So they're showing this image of a black hole, and this is not really what it is. A black hole is if you had taken the sun, our sun, and collapsed it down to, I think Phil says, 3.5 feet in diameter, that massive amount would be so dense, so tightly compact, that it wouldn't be emitting light anymore. It would be absorbing light. But what really happens is, if we were on our Earth at the time, we wouldn't be falling into it because its gravitational profile, and that's what I'll use, remains the same. It doesn't get any bigger. It doesn't go hunting other planets. It doesn't go galloping through the universe trying to find things to eat. As a general statement. There may be exceptions because I don't fully understand it. Anyways, it's not this big funnel thing that you get near event horizon, which is the point that if you get to that point and cross over, you can't get out. You're gonna go down. And anyways, so it's not this. It's a void. It has so much gravity that it absorbs light. As a consequence, if you were to take a photo of it, you would either see a void of light or a really interesting scenario. And the scenario is this, and as I said, I'm not a pro at this. I'm not an expert. I just read. I don't fully understand what Phil is telling me, but I think I have a general idea. And you can actually see this during an eclipse. You can see stars that are behind the sun during a total solar eclipse, and that's because the light from the star is coming at our sun, and our sun pulls it. Now that light would be coming in a straight ray, and if it didn't change, it would bypass us. However, the gravity of our sun pulls it around, arcs it, and now we can see it even though it's behind the sun. Kind of interesting. Okay, so a black hole has such immense gravity that when we look at it, we're going to be able to see the light from stars that are on the other side of the black hole, things that we shouldn't be able to see. If this was a normal star, we probably may not be able to see it. We may be able to see it. All depends. So we're generally going to see a void, but we'll see things behind it, not totally, but we'll as this black hole moves in front of other light sources, we'll see those light sources, those light rays initially bend, and then when it gets past the bend point, they'll blank out and it'll be a black void. And then as the black hole moves, or we move, we get back into the parameter where we can see the bent light. So black holes aren't these funnels. They're spheres, they're orbs. They're extremely tense, extreme gravity. And if we are in a normal position, if we took our sun down to, say, I think it's 3.5 feet, and crunched it down to 3.5 feet, its mass would have such a gravitational pull that would be absolutely amazing. But where our Earth is, we'd still be okay. Now, we'd be cold, we'd be frozen because our sun's not putting out any more light, any more heat, but we wouldn't be sucked in. So, what would happen? That's how I understand this, and I would encourage you to, if you're into astronomy, if you're into Star Wars, if you're into Star Trek, Battlestar Galactica, a number of other of the space sci-fi series, maybe read this book and get your own understanding of this, because I can't tell you that everything I've said in this book review is accurate or correct. I can just tell you that I read the book, I found it really interesting. I probably understood 10, 15, 20% of it, but I really enjoyed it, and I built this book review because in a couple of weeks, in a couple of days, we're actually going to go on another stargazing tour and go out to where we don't have light pollution, and we're going to go stargazing. Anyways, I love astronomy. We sit out in the backyard and use our telescopes or our constellation guides and find constellations and satellites and stars and whatever else, and really enjoy the evening. Hey, I had fun putting this one together. Thanks for watching, and I hope you enjoyed it. And I got an email, something from YouTube the other day that said, if you really like these, subscribe. I generally don't ask people to subscribe. I just let that go. Thanks for watching. Hope you enjoyed it.